This is the H.S. Denison, the world's first open ocean hydrofoil vessel. Overall hull length, 104 feet. Maximum takeoff weight, 95 tons. And design speed, 60 knots. The foil system selected for the Denison, 2 forward surface piercing foils and a fully submerged aft foil, is an inherently stable system in heave, roll, yaw, and pitch. 2 water jet pumps will propel the vessel during displacement operation. Commissioned and launched as a test vehicle June 5, 1962 by the United States Maritime Administration, it was designed and constructed by the Grumman Aircraft Engineering Corporation at Bethpage, Long Island. Operation of the vessel is accomplished by a captain, first officer, and engineer stationed in the pilot house. All systems and equipment are remotely controlled from this location. During the displacement operation, the 2 water jet pumps of the Denison are driven by a General Electric T-58 gas turbine. The pumps provide thrust by discharging high-velocity water streams below the displacement water line. Speeds in excess of 11 knots were obtained during the first trial run, which occurred 4 days after launch. In order to utilize a simple aft strut retraction system, the propeller pod was allowed to trail in the water during displacement operation. Testing has proven that the effects of trailing the pod are negligible. Foil-borne operation was successfully attained during the Denison's first attempt after 2 days of taxi trials. Speeds of 59 knots were reached during the first foil-borne operation. This achievement was made possible by the intensive test program undertaken by Grumman engineers. The whirling tank facility permitted engineers to study the erosion characteristics and dynamics of foils flying at velocities up to 100 knots. Besides operating at full-scale speeds, the tank tested the foils at variable angles of attack, varying yaws, and varying immersions. The pendulum facility was developed to measure the foil's lift, drag, side load, and pitching moments. As part of the overall study of hydrofoil construction, investigations into the flutter characteristics of struts were undertaken at Langley Field, Virginia. Here, the high-speed camera reveals the remarkable effect that velocity and water have on a solid metal. This effect being yet another challenge which engineers had to face and overcome with each new design. Construction of the hull was initiated in the Grumman facility at Bethpage, Long Island. The lightweight hull is a design using aluminum structure and skins throughout. In general, the hull is constructed similar to an aircraft fuselage, with continuous longitudinal stringers tied to bulkheads and frames along their length. The Great Expectations, a 1/5 scale model of the Denison, was built to serve as a dynamic test model of the larger ship. Intensive study of the takeoff and flight characteristics of this manned model continued even as the Denison's final construction was underway. The vessel is autopilot controlled. The flaps of the forward subcavitating foils, operating in conjunction with the fully movable variable attack tail foil, provides the pilot with mastery over roll, pitch, heave, and yaw. The Denison has been framed out, skinned, and decked over preparatory to transfer to the shipyard. The colorings on the vessel represent the prime metal protection system, zinc spray on the bottom and an epoxy paint on the top sides. The steel tail strut will support the gearing for the over-the-stern drive. Housed in the lower pod will be the lower gearing, propeller shaft, and variable attack tail foil. The gearing for the interior of the rear foil section was developed by General Electric at Lynn, Massachusetts. A simulated gearbox was built to study the relationship of the bevel gears to each other. The gears are fully loaded so that after studying the tooth imprint patterns, corrections can be made prior to its incorporation in the strut. A General Electric MS-240 gas turbine engine propels the Denison. It is a J79 jet engine with the afterburner removed and a free gas turbine coupled to it to turn the propeller shaft. The engine develops 14,000 continuous horsepower. However, at 60 knots, the Denison uses only about 8,500 horsepower, or approximately 2/3 of the engine output. The development of the propeller for the Denison was a project of the David Taylor Model Basin in Washington. This is a model of the supercavitating propeller that is used. It is put into the test tunnel where the high-speed experiment will aid in developing propeller efficiency. The supercavitating propeller is essential to the hydrofoil program as it can absorb horsepower at a high RPM. The propeller of the Denison is required to develop 25,000 pounds of thrust to maintain 60 knots. The main foils of the Denison are steel structures weighing about 5.5 tons each. They are hung from hinges, which incorporate shear points, and are retracted or extended by hydraulic cylinders. Since the foils are exterior to the hull, severe impact will cause them to break clear of it, creating no damage to the ship proper. The rear strut and pod assembly with the transmission installed weighs approximately 7.5 tons. During construction, the Denison's captain, William Clarke, kept a constant check on the ship's progress. The interior of the vessel can be used mainly for payload, since the main engine and shafting are located on the main deck. The after engine compartment contains the T-58 gas turbine engine, which drives the water jets for displacement propulsion. The salt water system provides for ballasting, bilge eductor pressure, transmission lubricating oil cooling, sanitary and deck hose services. The hydraulic retraction system permits the raising and lowering of the main foils whenever required, whether for leaving or entering port or laying alongside. All systems are color-coded for ease of identification: purple for JP5 fuel, red for firefighting, light blue for fresh water. Speeds of 62 knots were attained during the first week of foil-borne trials. Maneuvering characteristics were found to be excellent, with the ship capable of turning on a 400-yard diameter circle at approximately 50 knots. Lift-over-drag ratios, slightly in excess of 7 at 60 knots and 10 at 40 knots, have been measured during the early trials. The Denison is now embarked on a test and evaluation program. Data recorded during this phase is expected to greatly advance the state-of-the-art of hydrofoil design. And operational experience gained during the program is expected to prove the worth of hydrofoil craft in future open water applications.